there is a new fusion reactor set to light up before the end of this month.
This is the record-breaking reaction. It is more than 150 million degrees centigrade.
Nuclear fusion holds a mesmerizing promise that surpasses conventional imagination. It has the potential to ignite stellar power, offering virtually boundless energy with zero carbon emissions. German scientists just confirmed they've made a gigantic breakthrough in their latest nuclear fusion reactor that astounds the entire industry. If we can replicate it on Earth, it could transform our energy landscape. But how exactly does this reactor work, and how does it compare to other reactors? Join us as we dive into details on how Germany's new nuclear fusion reactor shocks the entire industry. Germany's building its own sun. Germany has just created a reliable and affordable energy supply, and it is a huge opportunity to solve all of our energy problems. Thanks to its excellent research landscape and strong industry, Germany offers excellent conditions for the construction of fusion power plants. The Wendelstein 7X reactor is an experimental stellarator built in Greifswald, Germany, by the Max Planck Institute for Plasma Physics and completed in October 2015. Its purpose is to advance stellarator technology. Though this experimental reactor will not produce electricity, it is used to evaluate the main components of a future fusion power plant. It was developed based on its predecessor, the Wendelstein 7AS experimental reactor. As of 2023, the Wendelstein 7X reactor is the world's largest stellarator device. After 2 successful operation phases ending in October 2018, the reactor was taken offline for upgrades. The upgrade completed in 2022. New fusion experiments in February 2023 demonstrated longer confinement and increased power. The goal of this phase is to gradually increase power and duration for up to 30 minutes of continuous plasma discharge, thus demonstrating an essential feature of a future fusion power plant: continuous operation. But what are the details of this clean energy source? Stick with us and find out. The Wendelstein 7X device is based on a 5-field period Helios configuration. It is mainly a toroid, consisting of 50 non-planar and 20 planar superconducting magnetic coils, 3.5 meters high, which induce a magnetic field that prevents the plasma from colliding with the reactor walls. The 50 non-planar coils are used for adjusting the magnetic field. It aims for a plasma density of 3 times 1020 particles per cubic meter and a plasma temperature of 60 to 130 megakelvins. The W7X is optimized according to the quasi-isodynamic principle. The main components are the magnetic coils, cryostat, plasma vessel, diverter, and heating systems. The coils are arranged around a heat-insulating cladding with a diameter of 16 meters, called the cryostat. A cooling device produces enough liquid helium to cool down the magnets and their enclosure to superconductivity temperature. The coils will carry 12.8 kiloamps of current and create a field of up to 3 teslas. The plasma vessel, built of 20 parts, is on the inside, adjusted to the complex shape of the magnetic field. It has 254 ports for plasma heating and observation diagnostics. The whole plant is built of 5 nearly identical modules, which were assembled in the experiment hall. This success led to their new funding program, named Fusion 2040. Research on the way to a fusion power plant is paving the way to the first fusion power plant in Germany. Germany's aim is to build an ecosystem of nuclear fusion made up of industry, startups, and science so that a fusion power plant in Germany becomes a reality as quickly as possible. In September last year, Stark-Watzinger announced that Germany would significantly increase research funding for fusion with an additional 370 million euros over the next few years. Together with funds already earmarked for research institutions, the ministry will provide more than 1 billion euros for fusion research by 2028. In August 2011, the 13th Amendment of the Nuclear Power Act came into effect, which underlined the political will to phase out fission nuclear power in Germany. As a result, 8 units were closed down immediately. So what is this fusion reactor? Why are the Germans so keen? Let's talk about this. A fusion reactor is a device used to produce electrical power from the energy released in a nuclear fusion reaction. Since the 1930s, scientists have known that the sun and other stars generate their energy through nuclear fusion. They realized that if fusion energy generation could be replicated in a controlled manner on Earth, it might very well provide a safe, clean, and inexhaustible source of energy. The 1950s saw the beginning of a worldwide research effort to develop a fusion reactor. The substantial accomplishments and prospects of this continuing endeavor are described in this video. The energy-producing mechanism in a fusion reactor is the joining together of 2 light atomic nuclei. When 2 nuclei fuse, a small amount of mass is converted into a large amount of energy. Energy, E, and mass, m, are related through Einstein's relation, E equal to mc squared, by the large conversion factor c squared, where c represents the speed of light, which is about 3 times 108 meters per second. Mass can also be converted to energy by nuclear fission, the splitting of a heavy nucleus. This splitting process is used in nuclear reactors. Fusion reactions are inhibited by the electrical repulsive force, called the Coulomb force, that acts between 2 positively charged nuclei. For fusion to occur, the 2 nuclei must approach each other at high speed in order to overcome their electrical repulsion and attain a sufficiently small separation so that the short-range strong force dominates. For the production of useful amounts of energy, numerous nuclei must undergo fusion, that is to say, a gas of fusing nuclei must be produced. In a gas at extremely high temperatures, the average nucleus contains sufficient kinetic energy to undergo fusion. Such a medium can be produced by heating an ordinary gas beyond the temperature at which electrons are knocked out of their atoms. The result is an ionized gas consisting of free negative electrons and positive nuclei. This ionized gas is in a plasma state, the 4th state of matter. Most of the matter in the universe is in the plasma state. At the core of experimental fusion reactors is a high-temperature plasma. Fusion occurs between the nuclei, with the electrons present only to maintain macroscopic charge neutrality. The temperature of the plasma is about 100 million kelvins, which is more than 6 times the temperature at the center of the sun. A plasma loses energy through processes such as radiation, conduction, and convection, so sustaining a hot plasma requires that fusion reactions add enough energy to balance the energy losses. In order to achieve this balance, the product of the plasma's density and its energy confinement time, which is the time it takes the plasma to lose its energy if unreplaced, must exceed a critical value. Stars, including the sun, consist of plasmas that generate energy through fusion reactions. In these natural fusion reactors, plasma is confined at high pressure by the immense gravitational field. It is not possible to assemble on Earth a plasma sufficiently massive to be gravitationally confined. For terrestrial applications, there are 2 main approaches to controlled fusion, namely magnetic confinement and inertial confinement. So, how do these confinements work to help harness the power of the sun? Stay tuned as we explain this process. In magnetic confinement, a low-density plasma is confined for a long period of time by a magnetic field. The plasma density is roughly 1021 particles per cubic meter, which is many thousands of times less than the density of air at room temperature. The energy confinement time must then be at least 1 second, i.e., the energy in the plasma must be replaced every second. But in inertial confinement, no attempt is made to confine the plasma beyond the time it takes the plasma to disassemble. The energy confinement time is simply the time it takes the fusing plasma to expand. Confined only by its own inertia, the plasma survives for only about a billionth of a second. Hence, break-even in this scheme requires a very large particle density, typically about 1030 particles per cubic meter. which is about 100 times the density of a liquid. A thermonuclear bomb is an example of inertially confined plasma. In an inertial confinement power plant, the extreme density is achieved by compressing a millimeter-scale solid pellet of fuel with lasers or particle beams. These approaches are sometimes referred to as laser fusion or particle beam fusion. How did this reactor come into development? What does it take to develop a fusion reactor? The fusion reaction that is least difficult to achieve combines a deuteron with a triton. Both nuclei are isotopes of the hydrogen nucleus and contain a single unit of positive electric charge. Deuterium and tritium fusion thus requires the nuclei to have lower kinetic energy than is needed for the fusion of more highly charged, heavier nuclei. The neutron, lacking electric charge, is not affected by electric or magnetic fields and can escape the plasma to deposit its energy in a surrounding material, such as lithium. The heat generated in the lithium blanket can then be converted to electrical energy by conventional means, such as steam-driven turbines. The electrically charged alpha particles, meanwhile, collide with the deuterons and tritons and can be magnetically confined within the plasma, thereby transferring their energy to the reacting nuclei. When this redeposition of the fusion energy into the plasma exceeds the power lost from the plasma will be self-sustaining, or ignited. Although tritium does not occur naturally, tritons and alpha particles are produced when neutrons from the DNT fusion reactions are captured in the surrounding lithium blanket. The tritons are then fed back into the plasma. In this respect, DNT fusion reactors are unique as they use their waste to generate more fuel. Overall, a DNT fusion reactor uses deuterium and lithium as fuel and generates helium as a reaction byproduct. Deuterium can be readily obtained from seawater. About 1 in every 3,000 water molecules contains a deuterium atom. Lithium is also abundant and inexpensive. In fact, there is enough deuterium and lithium in the oceans to provide for the world's energy needs for billions of years. With deuterium and lithium as the fuel, a DNT fusion reactor would be an effectively inexhaustible source of energy. Germany's Federal Research Minister, Bettina Stark-Watzinger, said the energy crisis has shown us how important a clean, reliable, and affordable energy supply is, and fusion is a huge opportunity to solve all of our energy problems, and it's inexhaustible. Thanks to its excellent research landscape and strong industry, Germany offers excellent conditions for the construction of fusion power plants. But what about the old energy source? Germany aims to phase out the use of fossil fuels by 2045 and switched off its last 3 nuclear power plants, which used conventional fission, after years of lobbying by environmentalists. This is understandable considering the harm that fossil fuels do to our environment. Stark-Watzinger made it clear that she doesn't want a return of the old-style nuclear reactors, despite calls for that from some within her Libertarian Free Democratic Party. She added that nuclear fusion, which works by merging atoms to release energy, wouldn't pose the same risks of uncontrolled meltdowns and long-lived radioactive waste that come from splitting atoms. This clean bill of health has paved the way for fusion reactors. How will nuclear fusion change everything? Once the nuclei come within a very close range of each other, the attractive nuclear force between them will outweigh the electrical repulsion and allow them to fuse. For this to happen, the nuclei must be confined within a small space to increase the chances of collision. In the Sun, the extreme pressure produced by its immense gravity creates the conditions for fusion. Ever since the theory of nuclear fusion was understood in the 1930s, scientists, and increasingly engineers, have been on a quest to recreate and harness it. That is because if nuclear fusion can be replicated on Earth at an industrial scale, it could provide virtually limitless, clean, safe, and affordable energy to meet the world's demand. Fusion could generate 4 times more energy per kilogram of fuel than fission that is used in nuclear power plants, and nearly 4 million times more energy than burning oil or coal. Fusion fuel is plentiful and easily accessible. Deuterium can be extracted inexpensively from seawater, and tritium can potentially be produced from the reaction of fusion-generated neutrons with naturally abundant lithium. These fuel supplies would last for millions of years. Future fusion reactors are also intrinsically safe and are not expected to produce high-activity or long-lived nuclear waste. Furthermore, as the fusion process is difficult to start and maintain, there is no risk of a runaway reaction and meltdown. Fusion can only occur under strict operational conditions, outside which the plasma will naturally terminate, lose its energy very quickly, and extinguish before any sustained damage is done to the reactor. Importantly, nuclear fusion, just like fission, does not emit carbon dioxide or other greenhouse gases into the atmosphere, so it could be a long-term source of low-carbon electricity from the second half of this century onwards. Is this new nuclear fusion reactor really hotter than the sun? While the sun's massive gravitational force naturally induces fusion, without that force, a temperature even higher than that in the sun is needed for the reaction to take place. On Earth, we need temperatures of over 100 million degrees Celsius to make deuterium and tritium fuse, while regulating pressure and magnetic forces at the same time for a stable confinement of the plasma, and to maintain the fusion reaction long enough to produce more energy than what was required to start the reaction. While conditions that are very close to those required in a fusion reactor are now routinely achieved in experiments, improved confinement properties and stability of the plasma are still needed to maintain the reaction and produce energy in a sustained manner. Scientists and engineers from all over the world continue to develop and test new materials and design new technologies to achieve net fusion energy. There are a lot of positives, but what does a nuclear fusion reactor mean for our environment? How much impact would this innovation have on our ecosystem? Fusion is among the most environmentally friendly sources of energy. There are no carbon dioxide or other harmful atmospheric emissions from the fusion process, which means that fusion does not contribute to greenhouse gas emissions or global warming. Its two sources of fuel, hydrogen and lithium, are widely available in many parts of the Earth. What then has nuclear fission been doing to our environment? Both are nuclear processes, in that they involve nuclear forces to change the nucleus of atoms. Chemical processes, on the other hand, involve mainly electromagnetic force to change only the electronic structure of atoms. Fission splits a heavy element into fragments, while fusion joins two light elements, forming a heavier element. In both cases, energy is released because the mass of the remaining nucleus is smaller than the mass of the reacting nuclei. The reason why opposite processes release energy can be understood by examining the binding energy per nucleon curve. Both fusion and fission reactions shift the size of the reactant nuclei towards higher bounded nuclei. But nuclear fission power plants have the disadvantage of generating unstable nuclei. Some of these have been radioactive for millions of years. Fusion, on the other hand, does not create any long-lived radioactive nuclear waste. A fusion reactor produces helium, which is an inert gas. It also produces and consumes tritium within the plant in a closed circuit. Tritium is radioactive, but its half-life is short. It is only used in low amounts, so unlike long-lived radioactive nuclei, it cannot produce any serious danger. The activation of the reactor's structural material by intense neutron fluxes is another issue. This strongly depends on what solution for blankets and other structures has been adopted, and its reduction is an important challenge for future fusion experiments. Can fusion cause a nuclear accident? No, because fusion energy production is not based on a chain reaction, as is fission. Plasma must be kept at very high temperatures with the support of external heating systems and confined by an external magnetic field. Every shift or change of the working configuration in the reactor causes the cooling of plasma or the loss of its containment. In such a case, the reactor would automatically come to a halt within a few seconds, since the process of energy production is arrested, with no effects taking place on the outside. For this reason, fusion reactors are considered to be inherently safe. When is electricity generated through fusion expected to be available? At present, fusion devices produce more than 10 megawatts of fusion power. ITER will be capable of producing 500 megawatts of fusion power. Although this will be on the scale needed for a power station, there are still some technological issues to address before a commercial power plant can operate. A prototype of a fusion reactor is expected to be built by 2040. Electricity generation and exploitation are also expected to take place in the second half of the century, depending on funding and technical advancement. Commercial fusion energy has been making headlines since scientists at the Lawrence Livermore National Laboratory in California achieved what many have said was impossible: a fusion experiment that created a net energy gain. Commercial fusion energy alone is exciting, but consider the ripple effect of how a shift in energy supply can affect industry and our environment. A number of clean and important inventions have lagged because of high energy costs. It'll take years to get there, but at fusion's fullest capacity, anyone will be able to use as much electricity as they need, with no environmental costs and very little expense. Fusion energy is arguably the most exciting human discovery since fire. Here's just a glimpse of how fusion power could help change the world. That ability could come from commercial fusion energy, creating a game changer for desalination by taking the energy overhead costs of desal and cutting them to nearly zero. Energy costs for desal are so high that plants sit idle more often than not. A desal facility built in Santa Barbara, California, during a drought in the early 1990s, for example, only ran for a few months before being mothballed for over 20 years. One problem was that the process, which usually involves distilling seawater multiple times until all the salt is removed, uses an incredible amount of energy. Even in a drought, when freshwater supplies are scarce, it's not cost-effective to run most desal plants because of energy costs. Take the $140 million desalinated plant in Dana Point, California, that won approval in 2022. It could eventually cover half of the area's water needs, but the desalinated water is 20% more expensive per acre than imported water, which could mean water bills running to as much as $15 a month for residents. And there are further ripples to consider when access to water improves. With energy superabundance, desal would not only be able to keep California's desert cities hydrated, but those plants would also be able to supply irrigation for vast carbon sequestration projects across the arid world. We could plant vast forests where there is today only scrub, using desalinated water to power these living factories for capturing carbon. All you'd need is an energy fusion plant nearby to power it. For centuries, the location of any kind of mill or other factory in the US was predetermined. You had to build it alongside a river, with the current pushing through a water wheel. As technology developed in the early 1800s, turbine systems could power mills of all sorts. More recently, factories still need some proximity to high-wattage transmission lines that can supply large quantities of electricity. But with fusion power, industrial planning would be upended. Just about anyone could have as much energy as they need, practically anywhere. Factories could, for example, be located closer to the raw materials they rely on, or to the retail markets that goods are destined for, cutting down on transportation costs and carbon emissions. Reshoring manufacturing from Asia and overseas to the US already cuts down on emissions both from shipping and production. For example, Chinese factories often rely on coal-fired power plants. With fusion powering the factory, and the logistics infrastructure too, those reductions would be even greater. Fusion also means agriculture gets a major boost because there have been two major roadblocks to innovation in the agricultural sector. One is water access, which desalination may help depending on location, and the other is electricity costs. One new way we could grow food that would be more environmentally sustainable would be hydroponic vertical farms, if the need for electricity to power the grow lights and other necessary equipment weren't so high. Here too, fusion can supply the solution, potentially allowing for a vast reduction in the land use footprint of agriculture and shortening the supply chain for fruits and vegetables by growing them in indoor farms much closer to urban centers, if not within city limits. Currently, California's temperate climate and vast agricultural areas account for nearly half of U.S. fruit and nut production, and many crops are harvested immaturely in the West to ripen along the way to kitchen tables back east. Under the fusion-powered grow lights, hydroponically grown strawberries, lettuce, or other crops can be grown to maturity without the use of pesticides or other harsh chemicals. Detrimental issues that come with field-grown crops, such as runoff and topsoil loss, would be eliminated too. Organic, sustainable food powered by fusion energy, harvested when it's ripe and sold at an accessible price point, could offer another ripple effect of increased enthusiasm for eating tastier fresh foods and better health. There's also an entire hidden, energy-reliant infrastructure that exists between farms and your fridge, a vast expanse of refrigerated warehouses, trucks, and other transportation collectively known as the coldscape. It's because of this little-known bit of infrastructure that we can have year-round access to fresh bananas, tomatoes, and other fruits and vegetables that are somehow always right on the edge of ripeness when you buy them at the store. But all that cold air takes a lot of electricity to generate, making the coldscape a significant contributor to the food sector's carbon emissions. With fusion energy, those emissions could disappear, and the dramatic drop in cooling costs would make tropical fruits and out-of-season produce easier on your wallet too. Given how much is being invested in the fusion reactor industry, what can we expect in the coming years? The future of nuclear fusion plants. In the heart of Provence, some of the brightest scientific minds on the planet are setting the stage for what is being called the world's largest and most ambitious science experiment. The task at hand is to demonstrate the feasibility of harnessing nuclear fusion, the same reaction powering our sun and stars, at an industrial scale. To do this, the world's largest magnetic confinement chamber, or tokamak, is under construction in the south of France to generate net energy. The International Thermonuclear Experimental Reactor Project Agreement was formally signed in 2006 by the US, EU, Russia, China, India, and South Korea at the Élysée Palace in Paris. There are now more than 30 countries collaborating on the effort to build the experimental device, projected to weigh 23,000 tons and withstand temperatures of up to 150 million Celsius when complete. Meanwhile, here on Earth, two main methods are being explored to generate fusion. ITER's project is focused on the second possible route: magnetic confinement fusion. In the tokamak, the charged particles are confined by a magnetic field, except the highly energetic neutrons, which escape and hit the wall of the chamber, transferring their heat and thereby heating the water running behind the wall. Theoretically, energy would be harnessed by the resulting steam driving a turbine. The field has been investigating tokamak physics for around 70 years, since the first experiments were designed and built in Russia in the 1940s and 1950s. According to Pitts, early tokamaks were small, tabletop devices, and then, bit by bit, they get bigger and bigger and bigger because, in order to make net fusion power out of these things, they need to make one, as that's very big. The longer that we wait for fusion to arrive, the more we need it. So the smart money is, get it here as fast as possible. Thank you for watching. Share what you think in the comment section below. Remember to like, share, and subscribe to see more videos.